Good morning. We continue our geometric modeling course. And the topic of today's lecture are graphs and their applications in mathematics and computing. In fact, we see graphs very often in our daily life, but to realize it, we first need to understand their nature. The picture on this slide shows the structure of a computer network in the new field called web visualization. First of all, we need to define the notion of a graph, then consider some of graph properties and some special types of graphs. At the end, a practical problem solved using graph theory will be discussed. Technical meaning of graphs in discrete mathematics is a particular class of discrete structures that is useful for representing relations between elements of sets. The most common representation of graphs used in computing is a diagram, which consists of vertices represented as points and edges drawn as line segments, joining its end vertices. Often this diagram itself is referred to as a graph. A graph G consists of a set of objects V called vertices and another set E with elements called edges. Each edge in E is identified with an unordered pair of vertices. These vertices associated with the edge are called the end vertices of the edge. In the figure, the edge E1 having same vertex as both its end vertices is called a self-loop. There may be more than one edge associated with a given pair of vertices. For example, E4 and E5 in the figure. Such edges are referred to as parallel edges. A general graph can have loops and parallel edges. The notion of a graph is strongly connected with the notion of a relation. Relation R is a subset of the Cartesian product A times A. You already met with Cartesian product in previous lectures and quizzes. Cartesian product A times A includes all pairs AB of elements of A. The graph of it connects all the nodes with each other with edges. Look at the graph shown here. What is missing in this graph for A times A? I'll give you a few seconds to think. Recall the previous slide. Correct. Self-loops for all vertices are missed. Graph of relation R includes some subset of edges E belonging to Cartesian product of set of vertices. A graph that has neither self-loop nor parallel edges is called a simple graph. The shown simple graph has 5 vertices and 6 edges, all listed in the slide. We can define a simple graph in terms of relations. The set of vertices of a graph corresponds to the universe of the binary relation R. The set of edges consists of edges between A and B such that A are B. Moreover, the relation R is symmetric and irreflexive. A directed graph, or a D-graph, VE consists of a set of vertices V and a set E of ordered pairs of vertices. The difference is that the vertices are not equal in pairs. One of them is initial, another is terminal. This order is shown by an edge with an arrow pointing from the initial to the terminal vertex. For example, if V is a set of people, a directed graph can represent a statement x loves y for each pair of connected vertices. Again, a graph G consists of vertices V and edges E. The graph presented here can be an example of such a tricky love story. All vertices and edges are listed in the slide. Let us learn some relationships between graph elements. Adjacent vertices means connected vertices. If an edge E connects vertices U and V, then we say HE is incident with vertices U and V. Vertices U and V are endpoints of HE. The number of incident edges of some vertex is called the degree of a vertex. A vertex without any connections is called isolated vertex. A vertex with only one connection is called a leaf vertex or end vertex, and the edge incident with that vertex is called a pendant edge. Words degree and valency are synonyms in the graph theory. Let us consider an example. Count degrees for vertices of this graph. It is easy to see that vertex A has degree 2, vertex C has degree 4, vertex D is a leaf vertex, vertex E is isolated vertex, vertex F has degree 3, vertex G has degree 4. It is stated here that B has degree 6. How is it possible? Try to think about it for a while. Yes, the self-loop H contributes with 2 degrees to the final number. If you accept this assumption, then the next theorem holds for any graph. There is a handshaking theorem connecting the degrees of vertices with the number of edges. For a simple graph G with E edges, the sum of the degrees is 2e. Why is it so? An edge UV adds 1 to the degrees of the vertex U and the vertex V. Therefore, edge UV adds 2 to the sum of the degrees of G. Consequently, the sum of the degrees of the all vertices is 2e. For the shown example, it is easy to check that the sum of degrees is equal to 12 and the double number of edges is equal to 12 too. A consequence of the handshaking theorem is that there is an even number of vertices of odd degree in any graph. In our example, 2 vertices, D and C, have degree of 3. Let G be a direct graph, and let E be an edge of G, that is UV. Then we say that vertex U is adjacent to vertex V, and V is adjacent from U. Edge E comes from vertex U, and E goes to vertex V. Edge E connects vertices U to V. E goes from U to V. The initial vertex of E is U, and the terminal vertex of E is V. Let us consider 2 connected vertices, U to V. UV is a directed edge. U is the initial vertex. V is the terminal or end vertex. The integree of a vertex V is a number of edges with V as terminal vertex, meaning edges coming in it. The out degree of vertex V is a number of edges with V as initial vertex, meaning edges coming out of it. The degree of vertex V is the sum of its in degree and out degree. The formula shows the connections between in and out degrees with the number of directed edges. Total number of in degrees is equal to total out degrees and equal to the number of edges. The reason is that each directed edge UV adds 1 to the out degree of one vertex and adds 1 to the in degrees of another. Now we are going to consider several special graphs. Their names and special symbols are listed here. Empty and null graphs, complete graphs K sub n, cycles C sub n, wheels W sub n, and cubes Q sub n, bipartite graphs, complete bipartite graphs K sub m, n, star graphs S sub k. These 2 examples show that graphs are more powerful for description of emptiness than relations. Empty graph or endless graph has no edges. Null graph has no nodes. Therefore, using graphs we can define an empty relation on the known domain. A clique or a complete graph is such that for every 2 vertices there exists an edge connecting them. In other words, a clique is a graph in which every vertex is connected to every other vertex. The number of edges in a clique is equal to n multiplied by n-1 and divided by 2, as it's shown in the formula, where n is the number of vertices. Several cliques are shown in this slide. They have their names, such as K1, K2, and so on, derived from the number of their vertices. You see the definition of a complete graph again. I'd like to ask you the question, can E contain any edges connecting a vertex in V to itself? Think about it for a few seconds. The answer is no, and the reason for this lies in the word other from the complete graph definition. There is one more special type of graphs. Some examples of cycles are drawn here. How many edges are there in C sub n? Correct. C sub n has n edges. And one more question. What is the degree of every vertex? I think that the answer for such a hard question is obvious for you. Yes, it is 2. Let me continue with questioning. Can a cycle be a complete graph? What do you think? The answer is yes for graphs with 3 elements, and no for others. Welcome wheel graphs. By looking at the picture, you can clearly understand why is it a wheel. The wheel graph can be made from the cycle graph by adding y extra hub vertex and n extra edges. Okay, now you are pretty experienced in these questions. How many edges are there in W sub n? You're absolutely right. The number is 2 times n. And what is the degree of every vertex? And you're perfectly correct again. It is 3 for all vertices except the hub one. N-regular graphs are graphs with vertices having the same degree n. You can see the 3-regular graph in the picture. One more test is here. You need to answer these 2 questions for the following graphs. Are complete graphs regular? What about cycle graphs? And wheel graphs finally. I'll give you a few seconds to think. Let's look at the answers now. Complete graph, K sub n, are n-1 regular. Cycle graphs are 2 regular. And all wheel graphs are not regular except the W sub 3. In this slide you can see one more example of special graphs. It is n-cube. N-cubes are defined recursively. We start from just one node. The second member of this family can be obtained by copying this node and connecting it with its duplicate. Q2 comes from copying Q1 and connecting duplicates by new edges. Total number of vertices in Qn is 2 power n. Total number of edges is n times 2 power n-1. This slide contains the pretty animation of Q4 construction. Let's look at this one more time. Another special type of graphs is a bipartite graph. Its vertices are divided into 2 groups and edges connected only vertices from different groups, as it can be seen from the figure. For a football game, such a graph can show pairs of players from 2 teams who kicked each other during the game. It is convenient to use bipartite graphs for domains with 2 different kinds of entities. On this slide, you can see several examples of such modeled domains and relations. What do you think? Can there be more than one way of partitioning a bipartite graph into two parts with vertices from different domains? What kind of vertices allow us to do so? The right answer is yes. Isolated vertices can be put in either part. You can see an example in the figure. In this slide, you can see the definition of complete bipartite graphs. That is, there are m nodes in the left part, n nodes in the right part, and every node in the left part is connected to every node in the right part. Note that not every complete bipartite graph is complete. Again, let us answer a few questions together. K sub m, n has m plus n nodes and yes, m times n edges. You can accidentally face with bipartite graphs if you decide to study ancient works of Jesuits. Here is the Cartesian product of universal subjects and absolute principles. And the last special type of graphs I wanted to mention is a star graph. As you can see, it is a special case of complete bipartite graph, capital K sub 1, k. There are a few examples of star graphs. How can we create new graphs from the existing ones? The first option is to extract a subgraph of a graph. The second option is to combine several graphs into one. We always can extract a subgraph from a graph by selecting some of its vertices and some of edges, connecting only the selected vertices. We cannot include an edge in subgraph which starts or terminates in nowhere. For example, the cycle graph with 5 vertices is a subgraph of a complete graph. We have a special name for the cases as was shown in the previous slide. A subgraph that has the same vertex set as graph G is called a spanning subgraph. One can find cliques in a graph. A maximum clique is a maximum complete subgraph. We also can make a union of two graphs by combining all their vertices and all edges into one graph. The initial graphs become subgraphs of the new graph. A wheel graph can be represented as a union of a cycle and a star graphs. Next, we'll discuss how to represent a graph in a computer. There are several ways of doing this, such as adjacency lists, adjacency matrices, and incidence matrices. We also need to know the notion of the graph isomorphism. Two graphs are called isomorphic if they are identical except for their node names. The first option for graph representation is an edge list. Edge list is a list of pairs of connected vertices. Pairs are ordered if a graph is directed. In the slide you can see the edge list for the drawn graph. For many applications, it can be useful to assign weights to edges. A directed weighted graph with its edge list are presented in this slide. An adjacency list represents a graph by a simple table with one row per vertex listing its adjacent vertices. The first row of the shown table says that the vertex A in the figure has B and C as adjacent vertices. Adjacency matrix is a matrix made up of zeros and ones. Imagine that row I and column J correspond to ith and jth vertices. If there is an edge between these two vertices, then element of the adjacency matrix A sub ij equals 1. It is 0 otherwise. This graph has 6 vertices A, B, C, D, E, and F. We can arrange them in that order for both rows and columns of the adjacency matrix. Like this. Let's fill the first row. There is no edge AA, therefore the first element is 0. There is an edge AB. It means that the second element is 1. Then 0, 0, 1, 1. In the next row, we will have 1, 0, 1, 0, 0, 1. For the third row, 0, 1, 0, 1, 0, 1. You can stop video here and try to fill last 3 rows by yourself. When work is done, you find the matrix like this. Notice that this matrix is symmetric. That means A sub ij equals A sub ji. Why is it so? I think that after tons of questions in this lecture, you can easily answer this one. Okay, I hope you did. More formally, if an edge ij exists, then the matrix element ij is equal to 1. Notice that an adjacency matrix is symmetric for simple graphs. If a team I played with team J, it means J played with I as well. And the fact of loop's absence, we have already noticed it. The incidence matrix of a graph is a matrix filled with 0 and 1 digits. It has a row for each vertex and column for each edge. For example, the left graph has 4 vertices and 3 edges, and the incidence matrix has 4 rows and 3 columns. The matrix element VE equals 1 if HE is incident with vertex V. For the first graph, the H1 is incident with only vertex A. Therefore, we have 1, 0, 0 in the first row. The H2 is incident with only vertex B. Therefore, the second row is 0, 1, 0. The H3 is incident with only vertex C. The third row is 0, 0, 1. And the H4 is incident with all edges. Last row is made up of ones. It is time for practicing now. Stop the video and fill the second matrix. You should get this. For the last graph, you should obtain this. We asked you a lot of questions today. If you also have some, feel free to ask. See you later.